one of the overarching goals in modern astronomy is trying to figure out how galaxies form and evolve. And as we know, most galaxies in the universe are actually dwarf galaxies. And because they are intrinsically faint and pretty far away, it's pretty hard to study dwarf galaxies. But luckily, we have two that are close by. The clouds, and they're about 55 kiloparsecs away, and they're the largest satellites of the Milky Way and some of the closest. And if we put on our radio goggles, we can see the stream, which is about 1 billion solar masses in gas trailing behind them. And of course, this alludes to their close interaction with each other in the Milky Way and the fact that they actually have a lot of gas. So they each have about 1 billion solar masses in gas. And this also indicates that they've been forming stars for a long time and accumulating chemical abundances. So chemical abundances. Let's talk a little bit, go back to spectroscopy 101. How do we actually determine abundances? So the strength of stellar absorption lines depends on a number of things, mostly the star's effective temperature, the surface gravity, and then the overall metallicity of the star, the content of heavy elements, and then the abundance of the particular element you're looking at. So here is a temperature sequence, and we can see that the dominant absorption lines, the vertical dark features, vary with temperature. So when you're trying to figure out what the abundance is, right, we want to generate a synthetic spectrum and compare it to the observed spectrum. And we use a spectral synthesis package that internally figures out, right, how different energy levels are populated in atoms in the atmosphere and at different depths in the atmosphere. And then it figures out what particular lines look like, what their broadening looks like, and then it can create this nice synthetic spectrum. So the observed is in black, the model is in blue. And so we want to try and probe through parameter space until we find something that matches. So here's a little simple toy model where it's basically trying to fit first the temperature, and now it's going through the surface gravity, and then finally the metallicity until it finds a good match. So this is the simple, just 3 parameters, but you can also do this with different elements, magnesium, calcium, and so on. And since we're looking now at many thousands of stars, it's hard to, takes too long to run spectral synthesis for each one of these sets of parameters. So there are certain shortcuts that people take. But that's kind of the general idea. So what actually creates these elements? Let's talk for a second about galactic chemical evolution. So we start with some cold gas in a small segment of a galaxy. It collapses under gravity to form new stars. They go through their chemical evolution, creating new elements, heavier atoms in their cores. And then the most massive ones will go supernovae and eject all of those elements into the surrounding ISM, which then get reabsorbed in the next generation of stars, and so on it goes. And I'll be talking a little bit about alpha abundances, so I just wanted to mention quickly a little bit more details about those. So the alpha elements are some of them mentioned there: magnesium, calcium, silicon. And they're created through the alpha ladder. So we were adding helium cores, nuclei to elements in the core of the star, very massive stars, and then also through the subsequent supernova explosions. So the 2 supernovae that are relevant here are supernova type 2, or through massive stars collapsing at the end of their very short lives, and then supernova 1As. So one of the things to remember is that the massive stars, as soon as they are born, they live life very quickly, and they go through their life process and explode after just a few million years, while supernova 1As which mostly give off iron. It takes about 1 billion years for them to form because they explode. They're a binary system, and one of the components is a white dwarf. And so it takes 1 billion years for intermediate mass stars to evolve to become a white dwarf. So once you start having a star formation event, it takes about 1 billion years for that to kick in. So what does that look like in the abundance plane? So here's a common plot that you'll see where we have alpha abundances relative to iron on the y-axis. So this doesn't really matter what the overall metallicity of the star is. It's looking at the ratio of those two. And on the x-axis, we have overall metallicity, and over time, kind of we're moving to the right. So you can see that in early times, we're dominated by supernova type 2, right, high alpha elements. And over time, then the metallicity will increase. And once 1 billion years has passed, then supernova 1As turn on, and then you go down. So that's kind of the schematic. But one of the things that we find is that this can get shifted left to right. So if you have very high star formation rate early on, you'll get to a very high metallicity before you hit the 1As turning on. If you have a very low star formation rate, it'll be very metal poor before you hit that alpha E. All right, so what do the Milky Way's abundances look like? So this is what the Milky Way looks like. So we have 2 alpha populations, the high alpha population, which is kind of corresponds to thick disk. These are older stars. And we have the low alpha population, which corresponds roughly to the thin disk, which are younger stars. Now, the existence of these 2 populations and why there's this alpha bimodality is still debated and is a whole other talk. And actually, what's interesting is that if we look at M31, we don't see this kind of alpha bimodality at all. So this is new data from JWST NearSpec, which is very confusing. And again, its own talk. But I wanted to just mention that briefly when we compare this to the Magellanic Clouds, the MCs. So let's move to the MCs and see what has been done on chemical abundances. So Vanessa Hill's group, like over 10 years ago, did a bunch of observations with the VLT. They looked at a few fields, about 200 stars, and did the really first detailed chemical abundances of the clouds. So they found that the alpha elements, especially oxygen and magnesium, were lower than we find in the Milky Way. That both barium and copper were a bit weird. So barium was enhanced while copper was depleted. All right, so in the last about 10 years, there have been several very large systematic spectroscopic surveys, Apogee, GAIA-ESO, as well as GALA, and this has allowed us to do more systematic chemical abundance studies of the Milky Way, as well as other galaxies, dwarf galaxies. So I've been most heavily involved with Apogee. So first we used the 2.5 meter at Apache Point Observatory and used plug plates with 300 fibers and the near-infrared spectrograph you see there. Now in Sloan 5, we have these robots. I don't know if you can hear this. So we have this focal plane system built by Rick Foge's team at OSU, and we can reconfigure in about just a few minutes, and we have this now in the north and the south. So we'll be mowing the sky and getting high resolution infrared spectra of millions of stars. All right, but so Apogee started at APO back in 2011. And in 2017, we commissioned a copy in the Southern Hemisphere at LCO. This was really exciting for me because I wanted to study the Magellanic Clouds. So here is our MC survey. And it's the first large systematic abundance study of the clouds. So we had 5,000 RGB stars and 26 fields, which we then roughly doubled because of the pandemic. Then we integrated about 10 hours for each field to get a signal noise of 100. So this is what the abundances look like. So in orange, in the background, you see the Milky Way. And then you see the LMC on top in black. You can see it looks very different from the Milky Way. You can also see the alpha Ni, kind of the metal poor end. And we started comparing chemical evolution models to it. And you can see that it's hard to match it exactly, but we also found that the star formation rate was very, very low in the LMC compared to the Milky Way, about 50 times lower. And that even the chemical evolution models couldn't match the very metal-rich part. So in order to match that, we needed to add in this burst in the star formation history. And then the red line you can see matches it pretty well. So that star burst created a bunch of massive stars that created alpha elements and then also pushed the metallicities up. So this is a great time to switch to star formation histories. So what do they say about any starbursts? Oh, 1 second before I go there. So one of the weird things about the alpha Ni is if we compare the Magellanic Clouds to the rest of the dwarf galaxies, so we have star formation rate increasing basically upwards and mass to the left, they fall way off the trend of the other satellites. For their mass, their alpha Ni should be much more metal rich. And one of the reasons we think that this is because they formed in a low density environment and only recently fell into the Milky Way. So this is consistent with the first infall scenario. All right, so back to the starburst. So let's switch to star formation histories, and I'll try to come back to abundance again at the end. So how do we determine star formation histories for a galaxy? So if you remember, the simple stellar population varies very systematically in age and metallicity, and it has this unique shape. So that's for a single age and a single metallicity. But of course, a galaxy is forming stars continuously, and so we have basically all of these added together. But we can solve this by basically taking the CMD of a galaxy, like we see here, of the LMC, and you break it up into various regions that you're trying to focus on, and then you model it as a superposition of different populations, different ages, and different metallicities. So here's the best fit model and the residuals, and what you get out, right, is the star formation history, so the star formation rate versus look back time, and then also age and age metallicity relationship. So that's the general idea. So the first work, really detailed work in the star formation histories of the clouds, was done with HST observations. So these are very deep pencil beam observations. They have CMDs that get below the oldest main sequence turnoff. And so we have some work by Knut Olsen and Smeckerhain and others that got some early star formation history results, and we're already seeing that the star formation history was very bursty, especially in the last few gigayears. The first really systematic study over the face of the Magellanic Clouds was done by Dennis Saritsky and Jason Harris. They used the Great Circle camera that Dennis developed and used it at the LCO 1 meter swope telescope. And they used a single 2K by 2K CCD to create these maps and UV-VIR bands and obtained multi-band photometry for 29 million stars. And what they were able to do is, Jason developed the Starfish CMD code that was able to fit the star formation histories to all of the 3 different combinations together. And there's some beautiful maps that he has that I won't have time to show, but they're the global star formation histories of the LMC and SMC. And they found that between about 12 to 5 gigayears, there was this quiescent period. And then more recently, there was this dramatic event that happened that restarted star formation, and they also saw bursts, and particularly at 0.5 and 2 gigayears ago. All right, and then Noelia, Noel, and Carmen Gaillard performed pretty deep BNR photometry in 12 fields across the SMC. So this extends to larger radius than the Harrison-Zariski data. And they found several periods of enhanced star formation. So now at about 5 different ages, so 0.3, 2 different intermediate ages, 5 and 10 gigayears ago. And they also found a pretty stark bimodality between the east and western SMC, and mostly driven by the 1 gigayear age group. All right, we also have the VMC survey, and I think Maria Rosa will tell us much more about this, but this is a big near-infrared survey of the Magellanic Clouds. And they were able to produce spatial resolved star formation histories, which you can see here. So this is a range of ages from youngest to oldest. And one of the things that Harrison-Zariski found was that in the SMC had a ring structure, which they don't see in the VMC data. And also, as you can see here, the older populations seem much more regular and round, while the younger populations have a bit more irregular shape. All right, so SMASH is a survey that I led, and we had a group of about 40 different people. We got 50 nights on the Blanco 4 meter with the dark energy camera, and that's the area that we covered over there, about 200 fields with 400 million objects. And the catalogs were all released back in 2019. And one of the major goals of the survey was to do really deep star formation histories. So this is what the images look like. So there's the team that really led this effort. And Thomas Rees, he broke up the LMC data into this Voronoi tessellation, into these 232 independent bins, and then ran star formation histories for each one of them separately. And as some of you might know, you need to do loads of artificial star tests to make this work. That's really like the hardest thing to do star formation histories. Right, so we can now look at different spatial regions and figure out what their star formation histories look like. So here we have different radial zones. And so purple is the very center. And as we move out, it becomes green. And you can see this very clear outside-in scenario where the very largest star formation is happening in the inner part. And it's still not entirely clear why this is happening. Some people think that it's quenching due to ram pressure and gas being stripped off. It's not totally clear, but it's a very evident pattern. We can also look at the spiral arm, right? The LMC has a single spiral arm, which is up there in the northwest in the blue region. And Thomas looked at that region versus the symmetric region on the right side, on the left side, the red region, and found that they have a very different star formation history. So the blue down here has a very high star formation rate for the last 2 gigayears, and it seems that that structure has been pretty stable and in place for about 2 gigayears, and likely caused by close passage of the clouds with each other. All right, now Paul Masana, who I think is online. Hi, Paul. He did this also on the small Magellanic Cloud, and this was now broken up into 74 different regions. And here are the stellar mass fraction maps where light is more mass. And you can see that in the 2 gigayear age bin, there's just a whole bunch of stars being formed in that region, again, likely due to this 2 gigayear burst. And here's a comparison of the SMC in the top and the LMC at the bottom, again, split into a north and south region. And the dashed lines show these peaks in the star formation, which are really synchronized between the clouds. So especially the 2 gigayear, 1 gigayear, and about a half gigayear peaks. And we think this is due to close interactions of the clouds with each other. And here we can see the 2 gigayear starburst, which we saw in the chemistry as well. So it's exciting to see that in the 2 different independent lines of evidence. All right, now let's go back to chemistry now that we've talked a little bit about star formation histories. Let's go back to the apogee data in the Magellanic Clouds. So Josh Povik, one of my graduate students, worked on looking at ages and radial abundance gradients in the clouds. And this is our map of thousands of stars. And he was able to determine ages of star by star using the distances in the plane of the LMC, as well as the spectroscopic and photometric data compared to isochrones. And then we were able to look at these radial abundance gradients as a function of age. And it's very complicated, but here is this one final plot. Don't worry too much about the details. The gradient is on the vertical axis, right? They're negative, they're decreasing as you go outward. And they're grouped into different chemical abundance families. So we have alpha elements there, mainly in the middle. And one of the things you can see is that there's kind of this turnover behavior, that especially for the elements that I pointed out here. And what we think is happening is this is a result of the close interaction of the clouds with each other and this starburst of about 2 to 3 gigayears ago, which is seen in almost all of the elements, not just alpha elements. So we think this had a really dramatic effect on the Magellanic Clouds. So here, this is the LMC. So here's the same thing for the SMC. And it's a little bit more complicated. It's not quite as nice as the LMC, not as clear, but there are also various elements where you see a turnover. And if you try to figure out the age of that turnover, it seems to be, it seems to precede the LMC and be at about 3.5 to 5.5 gigayears ago, which I found a little bit surprising. I thought they would be the same age, but that's what comes out of the data. All right, now a year ago, 2 years ago, time flies. I don't remember. When did Gaia DR3 XP come out? It was pretty recently. Yes, thank you. So Gaia released this XP low resolution spectra of 200 million stars. And unfortunately, the catalog of derived stellar parameters was not that great at the time of the release, but Rene Andre and collaborators released a new catalog where they derived these for 170 million cool stars. And what's great is that you can, even with these low resolution spectra, you can pull out temperature effective gravity, surface gravity, and metallicity. And here you can see the variation with metallicity in the spectra. So Paul and I were very interested in using this in the MCs, especially in the periphery. So here's a metallicity map of the MCs. And you can see there's a lot of substructure around the clouds that have been seen for a while now. But now we can actually look at the metallicity trends. And over there is, on the right, is the radial metallicity gradients as you move out. In particular, we were interested in trying to figure out what is the metallicities of the various substructures and what are their origins. So Paul broke it up into different regions, and we looked at the metallicity distribution functions, which you can see there in the bottom right. And most of the substructures around the LMC had very LMC-like MDFs, while just 3 of them, so the 3 right around the SMC, they had broader distributions and looked more like the SMC. So it seems that most of the substructures come from the LMC and some around from the SMC. So we haven't yet found really clear evidence of like a decreted stream that we have seen a lot around in the Milky Way and the Milky Way halo. So most of this material seems to come from the MCs themselves that is likely stripped off from their interactions. All right, so I'll just conclude, right? So the LMC had a very slow initial star formation rate due to its quiescent environment. We saw from the star formation histories that there are multiple synchronous peaks, likely due to their interactions that caused starbursts, and we see this in the abundance gradients. There's this turnover in the radial abundance gradients. And then also looking at the MC periphery using the Gaia XP metallicities, it looks like most material comes from the LMC stripped off the disk, while some right around the SMC comes from the SMC. And that's it.
Awesome, thank you, David. Okay, so something I forgot to say before, when you ask a question, if you could please say your full name and affiliation, that would be much appreciated. And Rachel, if you could start, yeah, thanks. Okay, questions to David. Okay, we're gonna go here first. Oh, sorry, so Tavisha, my bad.
David, thanks for a really, Tavisha more than NYU. This was very informative for someone who's sort of getting into LMC and SMC. So you talked a lot about what's been done with the stars, whereas you showed that really nice radio footprint, which showed a much larger footprint. Has anyone looked into this with the gas and the dust and seen sort of maybe something more detailed about the more recent mergers or anything like that?
People looked at the gas and dust a lot. What particular were you thinking about?
Oh, I was wondering if it sort of tells us more about like maybe the most recent merger. Probably, I don't think you see anything else beyond that.
Yeah.
But do we have more detailed understanding of what that's like?
Yeah, so there's a whole separate section, I think, with people talking more about the gas and streams, but it looks like the most recent, or the second most recent interaction about gig a year or 1.5 gig years ago between the clouds was what really stripped out most of the material that formed the stream from the Small Magellanic Cloud. And then the most recent one, about 300 million years ago, that formed the bridge region. So yeah, a lot of the simulations are telling us kind of what's happened in the recent past. Yeah.
Great.
Cal Barger, Texas Christian University. So out of curiosity, are you able to make better constraints on the star formation histories? And if I can ask also, do you notice anything weird, wonky with the SMC? Because there's questions about whether or not that's like two galaxy kind of weird situation thing.
Yeah, so the ages, I would say that you know, the star formation histories themselves from the very deep multiband photometry gives us the most precise ages and star formation rates. I think these ages are still a little bit rough, but they at least give us the overall trends that we see, and I think that's consistent with, you know, these bursts, especially in the central regions of the Magellanic Clouds, causing this turnover. I haven't thought too deeply about the recent paper about the SMC being two galaxies and what that would say about the chemistry, but I think Claire Murray's going to talk more about that in a couple of days.
Neve Dora, University of Texas at Austin. Thanks for this beautiful review. I have a lot of references I need to read now. Perhaps a comment/question, and that is, you argued that M31 perhaps doesn't have a bimodality in the alpha over iron versus metallicity thing, and my comment would be just when we had so few stars in the Milky Way, we also did not know about the bimodality. Right, so we should be quite careful saying something from, you know, a couple of dozen stars.
Oh yeah. I mean, we've known about the alpha bimodality for a long time in the Milky Way, even when we had just a few hundred stars, and especially the low alpha sequence is very prominent. But yeah, we've done mock tests to see, you know, would we have seen the Milky Way like alpha modality in M31? But yeah, low number statistics, I understand.
Okay, one more question.
Alex Riley, Durham University. If you go back to, at the very end, the metallicity distributions in the different regions. So this is great, this is really cool. Can you invert the problem and only look at the very low metallicity stuff, and do any new substructures kind of pop out? Or is it does it kind of look like a mess?
Yeah, maybe. Oh man, this is so small. I have a movie where it shows. Let's see if I can do this. This is kind of an old movie, but Paul's working on a newer one. But this shows different, metallicity slices, and we've stared at this for a while, but we haven't seen anything obvious pop up. But maybe we should spend more time doing that.
Awesome. Okay, I think we're going to move on now to the next talk. We'll just thank David again. Everybody has any more questions? Put them on the Slack. There's a thread on there. You can carry on discussing. So our next speaker will be Rachel Beaton, who will be talking about
Doing something. Keyboard assistant. What? Slideshow. Yeah.
All right. Talking about chemical evolution. Okay. So
Let me see if this works.
yeah, the top button. Yeah.
Okay, perfect. Hi, my name is Rachel Beaton, and I am an assistant astronomer at the Space Telescope Science Institute. And I'm leading a group that is forming as we slowly hire all of my friends called Stars Still Interesting. We're still working on the title. And I'm presenting work from a group of people that have been working for a long time, including Matt Chatrone, Chris Hayes, who just started at Space Telescope, Sten Hasselquist, Emily Griffith, David Weinberg, and Tawny Sitt at The Ohio State. Their pictures will show up. They literally did all the work. I'm just here as the hype person and administrator. But I'm going to talk about the chemical evolution of the Magellanic Clouds, the MCs. And what we're going to do is try to also put that in context of the galaxy and lower mass satellites and other things to understand what might be unique or not unique. And to do that, I'm going to use the Apogee survey that David introduced. This is a map of everything. All these circles are where we observed with Apogee. And hidden in here is our sub-survey called APO-EG, the Apache Point Observatory Extragalactic Experiment, where we targeted 7 dwarf spheroidals, the Large Magellanic Cloud, Small Magellanic Cloud, the Sagittarius Core and Stream, and the Gaia GSE. And all of that is and the Milky Way all at one thing. So what this means is with one sort of data collection strategy, with one set of analyses, we can study all of these objects on chemical evolution planes and minimize systematics between studies, which are considerable, and compare across all of this work. And what we're going to do is talk about extragalactic chemical evolution, because that relates to star formation histories. It relates to the types of materials that are in the ISM, and put them together. And so the main thing to keep in mind, as David has already pointed out, is that in the alpha to iron diagrams like this, what you're seeing are the relative contributions between type 1a supernovae that are producing the iron and core collapse supernovae that are predominantly fueling the alpha. So if you just have type 1a supernova and nothing else happens, you make a lot of alpha early, and then you decline over time as you make more iron. If you have starbursts or anything interesting happen in your galactic life, you will get boosts in that alpha as your iron continues. If you have dilution, you will dilute the gas and kind of step backwards and then work forwards, and you'll get these sharp features. And so those are the diagnostics that we're going to use. Okay. And then to acknowledge, David put together this beautiful meeting in 2018 in Bozeman, and we got to go to Yellowstone. And this has been 6 years with that pandemic in between of work to put together this whole story. So long game, sometimes pays off. So Apogee looks at about 22 different chemical elements over the course of its spectrum. And these elements each cover different types of processes that go into chemical evolution. So the Big Bang, AGB stars, R&S process, core collapse supernova, and type 1a supernovae. So most elements, many elements, are produced in multiple processes. So you don't actually learn about that single process by studying that one element. You have to put them all together. Now, unfortunately, some of our most interesting elements have really weak lines or single lines that get messed up. So you can't actually make good measurements on them. So we have to kind of like cut out all of these. And then also there's some things that just didn't go well. So we cut out neodymium. Did I get that right? Neodymium? Okay, that's the one I always forget. And we had to cut out some other elements because they ultimately weren't successful. Now, Chris Hayes went back and actually recovered a huge number of these elements by doing a different, very special analysis. So I will show a little bit of results from that. And if you're ever curious about using Apogee data, because all of this data that I'm talking about is public and you can download it at your leisure, the documentation is really good and explains what elements to use. Now I'm biased because I wrote it, but it is there. What I showed here is consistent with here. See, unsuccessful, not attempted. And my favorite is deviant. All of that is explained. Documentation workshops are really fun. You come up with ways to call things. So in case you're familiar thinking about chemical evolution, and I showed you this already, we often talk about alpha elements, core collapse, against iron, which is supernova type 1a. But one thing in David Weinberg's epic pandemic opus, and part of work that he had started, but this is work that he did in our Apogee Science Fridays during the pandemic, was to recognize that actually the core collapse supernova are a much better time axis than supernova type 1a, because there's a delay between when a star that could be a supernova 1a is born and when it becomes a supernova 1a. So it's actually a very jumpy axis. So, you know, generally this is time, but it's actually like time, right? It's the enrichment is not timed necessarily with the star formation, whereas the core collapse supernova, because they're a prompt mechanism, they're a mechanism that happens pretty quickly after a star formation burst, this is much more representative of time. So he has flipped the diagram. So now we have magnesium on the x-axis, so core collapse supernovae. And then we're looking at the magnesium to iron ratio, which would be supernova type 1a. Okay, this is very confusing, but it makes a lot of sense at the same time. And then what you have is you have a sequence that had a lot of supernova 1as, and you have a sequence that didn't have a lot of supernova 1as. Okay. This is critical, because then if I have these sequences, I can use the supernova 1as in a really interesting way to understand chemical evolution. So again, I'm going to show you this diagram that I explained before. Remember the decline, again, the axes flipped, it's super confusing. And you have these bursts, and that's actually what it looks like. So what David put together was called the two-process model. And this is a fully empirical model, and you can tell he's a theorist in his heart. I find this so confusing. It makes no sense. The model makes sense to me, but this diagram is so hard. The idea is for each position, I can split that into a vector that's described by a 1a component and a core collapse component. Does it make sense? It makes sense, but what's cool is you can also arbitrarily add dimensions and continue to deproject onto those axes, right? You could add a third dimension and this framework expands. What's also cool is you can fit these contributions to multiple abundance patterns. So not just magnesium, but the other 12 or 15 elements in Apogee, because we know some of them move together and some of them don't. So while I've been explaining supernova 1A to core collapse, this model is actually making the assumption that there's some enrichment that happens quickly after a burst, probably core collapse, and there's something that happens delayed. And it makes no other assumptions about the physical process. Okay. Which is cool because we're not tying ourselves to yields, which are highly uncertain. We're not tying ourselves to timing because ages are really hard. We're just totally looking at chemical evolution space. Okay. So, two-process model, a prompt process, a delayed process. And with the 300,000 stars in the apogee sample in the Milky Way disk, you can fit the behavior extremely well and use your statistics. So you fit vectors, like I just showed, and then you can apply that model to different systems and look for deviations, which tell you where things are different between the disk and those objects and where things are the same, so where it doesn't matter. Okay. So I'm going to show some results from Tani's first paper, I believe, which is actually taking this Milky Way model and applying it to some things that we're used to thinking about, like open clusters. So here are a bunch of open clusters. And what's plotted here are all the elements that can be fit in this two-process scenario. And you predict the abundances for your system, and that takes into account the evolution of the system, everything. And what you plot here are just the deviations. So the blue points and the gold points are the deviations between this system and the Milky Way. And on these diagrams, if you can see it, are a bunch of little lines. And those little lines are showing individual stars because this sample isn't huge, but it gives you a sense of the predictive power. So perhaps not unsurprisingly, open clusters, which are formed out of the disk, look a lot like the disk. Surprise, but proven. You do see some interesting outliers. So cerium, which is an interesting element, is overabundant in some, and then you see places where the data is probably wonky, in like vanadium. Okay. We can do the same thing for globular clusters, and this is wild. So globular clusters have multiple populations internally, and so we see where we expect in the light odd Z. Yeah, the HUD Z, we see all this weirdness, right? And we also see huge scatter. And that's where we expect to see the signatures of the two populations. But interestingly, in some of these, we also see the high cerium, so the high S. So pretty cool. We recover what we expect in this model from our prior knowledge. And then we can apply this model to the dwarf galaxies. So we're only going to be able to apply to the two clouds, to Sagittarius and to the Gaia, Sausage, Enceladus, whatever you want to call it. And in this case, we can now look at where things are extremely different from the Milky Way. And in this instance, we are looking at, again, this stream of elements looks very strange, and in the cerium. Okay. Well, and these are a little odd too. And that's all really interesting. So the limitation, however, in this particular methodology is that we're limited to high metallicity populations because we're just training on the nearby solar neighborhood, the nearby disk. So this is only telling us what was different in the highest metal or the highest magnesium populations, as this might be. So yeah, I'm highlighting there what's really different. What should be striking to you is that all of these dwarfs have the same behavior, more or less. So whatever's happening is somewhat universal. And that typically, if you're getting cerium from AGB stars, you would also expect the C plus N to be enriched as well, because the C, and Byrne will cover that in his talk, I think. But they're not, they're anti-correlated here. So what Sten did is Sten took this work and decided, let's push our Milky Way modeling to lower metallicities so we can use as much of the dwarf galaxy sample as possible. So he worked really hard on this metal pore sample. In apogee, because of various reasons, the metal pore sample is very sparse. So this is actually really hard trying work. But that lets you use the entire span of the stars that were observed in apogee, and we're talking, thousands of stars in the larger objects and about 200 stars in Fornax. And this is showing you their alpha to iron distributions. And I wanted to show this to give you a sense for how different and weird the dwarf galaxies are compared to the disk. So the disk has the two characteristic sequences in gray. So there's the high alpha sequence and the low alpha sequence, and that's the alpha biomodality that we've talked about. But the dwarf galaxies entirely do their own special snowflake behavior, right? So they are offset entirely. In the LMC, you see that rise at the end, the starburst. In Sagittarius, you see a little starburst and then it's declining again. They're all showing these really fun behaviors that you can study in dwarf galaxies because of their shallow potential wells. But this is, again, only looking in that really simplistic space of one alpha element versus one supernova 1A element. So what we're going to do is we're going to train on the Milky Way again, and those are the black points, so they're all at 0. And we're going to look at the residuals. And so whether it underpredicts or overpredicts. And for this diagram, I've actually labeled where these elements come from visually, because I had enough space on the slide. And again, this is pretty much identical to what Tawny found, which is that for carbon plus nitrogen, sodium and aluminum, you have this very big difference. And nope. And over here, we have some differences that are, there's a lot of scatter here because these elements are less well measured. And again, the cerium is very high. So extending to metal poor, using a lot more stars, we get the same basic results. And you start to see a few little things pop up as well. The thing to keep in mind, though, is that actually so again, this is a magnesium. So magnesium to iron versus magnesium. So now we're looking at core collapse along the X. That the low 1A sequence in the Milky Way is extreme compared to basically almost everything happens in the dwarf galaxies, right? The dwarf galaxies are offset to even lower magnesium overall, lower core collapse. And because of that, why would we use these as our templates? Why wouldn't we just train on the dwarf galaxies? So that's what Sten did. And again, what we're showing is we're training on, I believe, Sagittarius, because it has the most stars. And then we're looking at the residuals between Sagittarius and the other objects. And now what we're seeing is that actually, if you just train on Sagittarius, that better predicts all the elements in the dwarf galaxies. This is kind of logically flowing, but it's really cool to do it for real. With the exception of the places where things were low before look high in the Milky Way, which is the black line. And these plots are super confusing because they're combining like so many dimensions of information. We've spent a lot of time trying to make them better, but it just gets more confusing visually. So the key information here is that now when we framed it in a different way, we're not saying the dwarf galaxies the dwarf galaxies all seem very consistent with each other. Whatever's happening in the dwarf galaxies seems very consistent. So maybe the weirdness is in the Milky Way. So let's think about what could be weird about the Milky Way. Yeah. Lots of mergers. Lots of mergers. Yes, that's correct. So what's cool about the two-process model, which I already told you, is we can just add a third dimension and we could fit that dimension. So for the longest time, we thought we're just going to have to add an AGB dimension to fit this cerium enrichment, because that comes from AGB stars. But when we looked at this plot, we're starting to realize what we actually have to do is fit a third dimension, which is a depletion. So in the Milky Way, when galaxies are merging and forming, the Milky Way is actually receiving gas at lower metallicity from its dwarf satellites, which is then mixing. And so what that does is it shifts you back on your metallicity axis and you start forward again. So Emily right now is coding up how to do a depletion event in the Milky Way disk to see if that better fits these residuals. And then we'll actually have information on how much dilution you need in the disk, which is trained off of these dwarf galaxies. And that is because when she added a third dimension of AGB stars, it just went, I believe the technical term is wackadoo. It doesn't make sense because you would need to enrich anything that came from AGB stars, which you specifically don't have, which is why I've been pointing that out over and over. So we find evidence for depletion in the Milky Way disk, which is known from other studies, but we're tracking it now in this multi-dimensional space. Okay. We can also start to look at cerium and neodymium because they're S and R process. And they're actually like a little bit of both, but you can play with it. And this is work that Chris did before starting at Space Telescope, where he went in and he basically did a second thesis during the pandemic. And he measured all these things independently. And so you can make plots like this, where you're comparing cerium to neodymium against iron. And he's showing the thin disk on the bottom and the thick disk at the top, which again, I switched terminologies on you. The thick disk is high alpha, the thin disk is low alpha.
Same.
What?
It's not the same, the thin and thick. High alpha and low alpha, these are the terms that you're talking about, right?
Correct. Yes.
It's not the same as thin and thick.
Yes. 5 minutes, okay. And so basically we can look at a pure solar process and a pure R process and see how these things behave over time, which is telling us how different processes are turning on across the Milky Way, which is interesting in itself. But we can also plot dwarf galaxies. So the large cloud is in gold and Sagittarius is in red. But we see Sagittarius, we see the large cloud actually hitting, going up to the solar S process sooner, which again is another indication that you need those S process stars, those AGB stars to contribute to the gas, which is cool. All right, but how are the clouds really different? So we can also look at things with lower stellar mass, and we can look at the 7 dwarves of ApoEG. And this will be in a bunch of papers by Matt Chatrone. We started out as 1 paper, it's now 3. But these are our 7 galaxies, again, all on the same scale. And we can separate these into the simple chemical evolution, where things are just declining over time, and the complicated evolution, where things are happening that are fun and exciting. Simple evolution, again, is basically they formed some starbursts, and then things decline over time, and that looks a lot like the Gaia sausage Enceladus, which we know merged like 10 gigayears ago. So what you're seeing is a depletion of all the gas, no more star formation, and they evolve. And then for the complicated ones, we're seeing, just like the LMC, this decline and then these starbursts. And sextants, I don't even know what that is. But of course, the interesting thing is, I mean, if you look in the lore, that these are all alpha high. But if you actually look at the detailed apogee results, they're, you know, alpha low, just like you see in the LMC. So here's the LMC, SMC, and Sagittarius in comparison. And again, you see the same behavior. It's just the timing of these bursts that changes. Now, what's cool, and this is a huge conceptual jump, is that we can take all of these trends and we can plot them on one diagram now. And we have no systematics going up and down. So this is 12 galaxies, alpha to iron, on one plot. And the dashed lines are the dwarf spheroidals. And then we have LMC, SMC, Sagittarius, and then the high alpha disk, the bulge, and the low alpha disk, all plotted there together. And I think you can stare at this forever. So we can separate by objects. This is a little cleaner. And we basically can see that, you know, LMC and Sagittarius are enriching, so they have longer enrichment histories and they're turning up. But it seems like by mass, a lot of things have these turn ups in these secondary bursts, which makes sense. But again, we're showing it very conclusively. You also see that these dwarfs look nothing like the disk. And so that tells you they're probably, if they're contributing, it's in gas or it's a very small level. And this is the thing I showed before. And I didn't note that this is actually tagged by mass, by stellar mass. And so you can see the impact in the chemistry, you see the impact of the star formation history. So the less massive things quenched earlier, things are able to go along longer and evolve. But what I call comparative dwarfology, these do not follow a single track. There's actually more going on in here, which is captured in that two process work. So this is tau 90, which is the time to delay to remove 90%, to build 90% of your mass. And so again, we see the things that can build mass longer get to higher metallicity on average, but you also have some really old systems that can enrich to higher iron, which is telling you that they had, something interesting happened in their early lives that allowed them to enrich that much. Again, compared to the rest of the sample. And the last thing, and this is my red string diagram, literally, is that you can't fit the ages. So these are the dwarf spheroidals, Sculptor and Carina. You can't put an isochrone down when you have alpha and iron evolving at the same time. They do not trace one-to-one with age or with metallicity. You have to include these trends if you want to get ages. There must be a simpler way for me to plot this, but the basic point is that these, you can't, when you have these things happening together, you can't just put down isochrones and walk away with ages, which is why Josh did not use isochrone ages in his paper. Okay, so comparing the chemical history of galaxies requires reducing systematics so that you don't have these offsets between systems. We can look at the detail of the Milky Way disk, massive satellites, and the dwarf satellites. Using the two-process model that is well-trained on the disk, we can see the evidence of a third or fourth process and start to fit that process as well. And we can also put a large dynamic range of galaxy mass on a single plot to start isolating what is unique about these systems and what is the same, to again study those together. And the decline in alpha colludes with the rise of iron in isochrone fitting. So be very careful with ages from giants that don't take that into account, which arguably is very hard because most of your isochrones are super alpha enriched down to no alpha enrichment. There's very few isochrones that have sub-alpha, which means the isochrones won't work for the young populations in the LMC. Okay, thank you.
Thank you very much, Rachel. That plot, the alpha iron playing with mass, like every time I see it, I'm just excited. So that's great. We have hands raised, questions. I'm gonna go here first. Name, please.
Oscar Jimenez Arranz from the CCUP, Barcelona. I have a question regarding on the plot that you show two-dimensional where David can show, like in the supernova one type and the other one. I have seen in the plot, they look that they are on orthogonal basis, no? So it is kind of degenerated. Can you expand a little bit on that?
Yeah, so, sorry. Yeah, so because they're not fully orthogonal, because no element is pure, what you have to do is you train on a set of elements where you can say this set of elements is, much more pure on this process or that process, which I didn't cover because it gets into the weeds quite a bit, but it's well explained in his 2022 paper. That's why it's 80 pages long. But yes, you have to fit to a set of elements that are well measured and that are predominantly coming from a process. Yeah.
Thank you.
Hi, Rachel. Christine McQuinn, Space Telescope and Rutgers University. So you had a plot a couple slides before this where you talked about adding another dimension, namely dilution. Have you thought about adding another dimension, namely outflows for the dwarf galaxies?
Yeah. So when we're doing the chemical evolution modeling, which is why I don't show dwarf by dwarf chemical evolution models, outflows and dilution, yeah, they all conspire in interesting ways. So yes, we are playing with outflows. The project that I want to start now, now that Chris is at Space Telescope, is to actually take chemical evolution models, synthesize some data where we put in an outflow or a dilution event or something, and actually study what the effects are in this and then fit the two process model vectors and actually study the effects to get some intuition when we're getting complex information showing the same effects, or when we're getting something that's very clean. So that's what we want to start playing with soon, to have that kind of information.
I
Yeah.
think that'd be really interesting too for the oxygen, which has got more of a cleaner nucleosynthetic origin, right? With just core collapse.
Correct. The oxygen is very hard in the optical. It's unique to the infrared as having a very clean measurement.
Eugene first, then.
Eugene speaking. When you were showing the plot of the different abundances for the globular clusters, carbon, nitrogen, sodium, aluminum were high than Milky Way. For dwarf galaxies, it was lower. Could I interpret it as Milky Way is kind of dwarfs plus a lot of globular clusters? So if you form something that is has little globular clusters, you'll have a dwarf-like abundances. When you add globular clusters, you'll have more Milky Way-like abundances. Or is it not working like this?
Right. So the interpretation of those specific features in globular clusters is that the first generation of stars is enriching the second generation of stars. And that enrichment is primarily going to be from massive stars producing elements and polluting the gas before the second set of stars forms, or the latter half of the low mass forming stars, because that takes longer. And so what it could be saying is that the globular clusters are able to hold on to those yields better. And when they throw those yields out, maybe they're sticking around in the disk. When the equivalent thing happens in the disk, they're sticking around. But in the dwarfs, they're losing them, which would be the Sallow potential well argument. However, there are about 10 different mechanisms that can produce the globular cluster enrichment. So whether that one mechanism could happen in all these different systems the same way is an incredibly interesting question that we're trying to isolate and then try to do timescales. So I showed that last thing with ages because everyone would be like, put times on it. And it's like, well, you can't yet. But it's possible that there are people working on these more interesting isochrone suites that take all these effects into account.